So last time we were discussing about data structures. Actually, we started by discussing data types, and we were looking at the different type of data types that exist in R, where we were talking about the likes of numerics, characters, and all that. Then we went ahead and we were discussing about data structures, and I was saying that we basically categorized them into two, where we were saying we have what we call the homogeneous data structures, and we were saying that the homogeneous data structures are those data structures that will only comprise of elements of the same data type. That is why we started by discussing data types. What are these various types of data? And then now we went ahead now discussing the data structures, and we categorized them into two: the homogeneous data structures and the heterogeneous data structures. Where we were saying homogeneous data structures are those data structures that are of elements of the same type. So if it's characters, then we are expecting all elements of that particular data structure to be characters, not a combination of characters and numerical. It won't be a homogeneous data structure. On the other hand, we were saying heterogeneous data structures are those data structures which comprises of elements of different types. And I was even giving an example and saying, suppose we have one example of a data structure. A heterogeneous data structure is what we call a list. So in a list, we can store elements of different data types. Like I can say Ali 22. Now Ali is the name and 22 is the age. Now that is not applicable now in homogeneous, because the two are of different data types. And we were even looking at an example where we are trying to create one with two different data types for a case of homogeneous, and we realized that R coheres it to one data structure. So the types of homogeneous data structures we were talking about are vectors, matrices, and also arrays, where we are saying vectors are one-dimensional data that is of same kind or type. Now matrices is two-dimensional, and vectors is arrays is more than two-dimensional, that is 3 and beyond. Now for the case of heterogeneous data structures, we said we have lists and data frame. So then we went ahead and we started discussing vectors as one type of homogeneous structures. So we actually discussed how we can create a vector, and we were saying that to create a vector we are using what we call the combine function. We were saying we were using the combine function. That is the function. Then now we say we list the elements of that particular vector, now separated by a comma except for the last element. Now again, we went ahead and we were looking at how we can access some elements of a vector, what we call vector subsetting, like Mary was saying. Now in vector subsetting, we are basically saying we need to use the name of that particular vector and a square bracket. Now in that square bracket, in most of the cases, we will be using the position of that particular element, or rather the index of that particular element in the vector, now to access. And if we want multiple elements, then we are using operators like this operator we were using to list the number of position and all that, in case they are consistent. And of course other several ways we discussed, as well as now trying to use logics and equivalence. And this arises as when Mary was asking, suppose we have marks and we have a number of students scoring 78. How can we access that? And that now brought the aspect of using logics and all that. I hope we are all good with that, and if not, the beauty is that we have a video on YouTube that you can actually review and try to remember everything. Now, in today's session, we still continue discussing homogeneous data structures, and more specifically, we will go to the second homogeneous data structure. That is now what we call a matrix. And remember, I was saying matrix is basically having two-dimensional. Now, the aspect that matrix has two-dimensional is because we are saying the matrix have rows and columns. I know we all know this, that a matrix has a row and a column. Now, because a matrix has a row and column, therefore it makes it to be a two-dimensional. So today here, we are going to discuss about matrices. That will be our first discussion, or rather our first data structure we are going to discuss as far as homogeneous data structures are concerned. Now, to create a matrix in R, again we use a function, and this function is called the matrix function. We use what we call the matrix function. You can see that function. The matrix function is actually found in the package known as base R. Now, base R is that one package which has all the basic functions, basic functionalities that you need to use in R are all found in base R. Now, what you do, you can as well check the documentation if need be. Remember that to always ask for help whenever you are in doubt. But for this class, we are not going to do a search because, okay, we know how to implement the function. But it's always good for a beginner to maybe look and have the documentation, because this is the syntax actually. You can see we have the data, the number of rows, the number of columns, and by rows and all that. You will see that as we implement. But basically we are saying, to create a matrix, we use the function matrix. We use the function matrix. So suppose, let's just take this from where we are, that is from vectors. Suppose I have a vector. Let's say the other day we are having a vector x, and this vector x maybe comprises of elements from 1 to 9. Now that is a vector. Is that vector correct in the first place? If I run that, yes, it is. It is storing elements from 1 to 9. But it doesn't look good. It looks good when you use the combine function. Now, when I call for x, you realize it will list all the elements that are contained in x, that have been stored in x on the vector x, which as well can be observed from the environment, that x is actually having integers starting from 1 to 9. So I want now, this is now a vector, I want now to have this as a matrix. Now what I'll do, I'll use the matrix function and now say, because I use the small x for the vector, I can decide to use a capital X and say capital X is actually a matrix of now, of what? Of now x. Basically what we are doing, we are taking these elements and now forming a vector out of these elements, and these elements are stored in x. So now it's like we are converting now the vector to a matrix, literally. Now we put a comma there and we say this is how actually we implement the function. First you have the data, like you can see here from the function documentation. Then you have the number of rows in that particular matrix, followed by the number of columns. Now based on our data set, we can actually form a 3 by 3 matrix, because we can divide these into 3 segments. 1, 2, 3, one segment, then 4, 5, 6, another segment, 7, 8, 9, another segment. So the number of rows, we can say that n rows, and you can see it's popping up. So you will say the number of rows is 3, comma. Now the number of columns, you see it's popping up, so you just select that and you say 3. So I have my vector, being converted to a matrix, and I'm assigning that matrix to capital X. Now this matrix I'm forming from the element 1 to 9 is having 3 rows and 3 columns, which we say it's a 3 by 3 matrix. So when I run that, now you realize my X has actually been converted to a matrix. So now when we call capital X, we are expecting it to be a matrix. Now when we call capital X, you can see it's a matrix here, and actually it's having the elements represented, or rather arranged in column wise. It's starting 1, 2, 3 column wise, then 4, 5, 6, 7, 8, 9, 7, 8, 9. So we have our matrix. We have actually made our matrix using the matrix function from the vector X. Now one thing you need to know, or rather one thing you need to take note, is that guys, I'm not actually monitoring the meeting as such, because you see I'm trying to be fast. At least we have 1 hour. So if you are left behind, if you have any question, or just you can just unmute and speak so that I can hear you, and I'll be able to respond. So I was saying that actually we don't have to form a matrix, a vector, then now try to convert the vector to matrix. Like, we could just have listed these elements in the matrix as we form the matrix and have it. This is what I'm saying. We can have our matrix capital X redefined, say that X is now from, of course we are using the matrix function because we want to define our matrix without forming a vector. So for the data, I'll have, it is starting from 1 to 9, then I put a comma there, and now I specify the number of rows and the number of columns. Now one thing you need to know is that the function, the arguments are arranged in that format as the function is defined here. So automatically R knows that we will always have the rows and the columns. So I don't even actually to start writing number of rows equals to 3, number of columns equals to 3. I can just simply write 3, then comma. I can just write 3. Okay, I didn't move the cursor, sorry. I can just write 3, like 3 here, then comma 3. By default, R will know that this is the number of rows, number of columns. There is a word for these arguments that are arranged in a certain order, and you can just pass them in that order. The name is not coming, but yeah, I'll get it as we proceed. So when I run that and I call X, I now have the very same matrix. So actually, there is no need of us starting by, creating a vector and then coming to do the matrix. I hope that is clear. Now one thing that you also need to know, guys, if I'm very fast, kindly you can say I'm very fast. One thing that you need to know is that in both cases here you can see that the matrix are formed such that they are arranged column wise. So we are starting 1, 2, 3, then 4, 5, 6, 7, 8, 9. Suppose that is not the desired order. Like, we don't want that order. We want them based on the matrix that we need to form. We want to have 1, 2, 3, row wise, then 4, 5, 6. How are we going to do that? Now to do that, it is very simple. On that function, you can see here on the function implementation, or rather documentation. So we have the number of rows, the number of columns, and then we have by rows. and by default it is false. Now by rows, this argument means that you are specifying the order in which the matrix want to be created. Is it by rows? Like we have 1, 2, 3, 4, 5, 6 row wise, and now it's false here, which means it will be column wise by default. So the only way to make it have them row wise, we need to change by row to true, not false. So again here I'll come, put a comma and say by rows, by row equal to true. Actually we don't have even to write the whole term. T represent for true. So when I run that and again call X, you can see now it's arranged in row wise. So I have 1, 2, 3, 4, 5, 6 and all that. I hope you guys are getting that, like how we create matrix. Is it clear? Hello? Oh yes.
Yes, it's clear.
Okay. Now again, just still under forming matrices, there is this one matrix which has the same elements. Like the entire matrix is made up of one element. What is the name of that matrix? Maybe you have a matrix of 2, 2, 2. What is the name of that matrix? Some mathematician. What is the name? What is the name of the matrix? What is a singleton matrix? But I think singleton is one-dimensional. Okay, but what I'm trying to say is, maybe we'll get the name. Suppose I have this one matrix which is made up of one element. Like let's say here we have 2, 2, 2, 2 all through. So how do we form such a matrix? Now you see that particular matrix, we don't have to list 2, 2, 2. Like here now you are writing 2 2's and then you specify the number of rows and the columns and all that. No. To have such a matrix, let's say we call it Y, we can just say Y is the matrix which is made up of elements 5, like we have 5, 5, 5. Now you put a comma, you specify the number of rows and the number of columns. So let's say it's a 2 by 3 matrix and you run that. So when I call Y, it is a matrix of only 5 elements with 2 rows and 3 columns. So R will take this to be the elements. Of course, they are the elements. And now the number of rows and the number of columns. So when we have only one element here, it will repeat it to have elements in the listed, in the specified number of rows and the number of columns. I hope that is clear. I hope that is clear for matrices. Now, one important thing is what we call, or maybe before we look at, there is also what we call a diagonal matrix, if I can remember. Now, a diagonal matrix is, you all know a diagonal matrix, is one matrix that has elements at the diagonal and zeros elsewhere. So to create a diagonal matrix, we use this function, the diagonal. function. Now this for this one, you need to specify what you need to have with the diagonal. Suppose I need to have 1. Now you specify the number of rows and the number of columns. So I can say 3 by 3 matrix, and I run that. Because I didn't give it a name, automatically it will give me the matrix. So you can see this is what we call a diagonal matrix. It has elements only on the diagonals and 0 elsewhere. So we can actually use this diagonal function to create a diagonal matrix. So when I say 2 at 3 by 3, I'll have 2's there. I hope that is also clear. Now, one very important thing that we need to ask ourselves before we even proceed to forming more and more matrices using other sophisticated ways is to ask ourselves, how can we access the elements of a matrix? Or rather, how can we subset a matrix? Like for instance, where this matrix X, let me just call the matrix X. Now suppose I want only these 2 elements, 5 and 6. How can I do that? Or suppose I want only this one element, 8, because it is only that element that I'll be using in my operation, in my analysis. How can I access such element? That is the question. Now that brings the aspect of subsetting a matrix. Now just like in vectors, in matrices, we will still be using the square bracket we were using. Of course, we need to have the name of the matrix and now the square bracket now. But now, unlike in vectors, where we were having the position, because it is only one dimensional, so we only have one position. In now matrices, you need to specify the number of the row and the column that you want to access those particular elements, and we'll be using the square bracket. So, and this can easily be illustrated by the matrix itself. When I call X here, you can see from this, you can see a hint that here I have 1. Remember, sorry, I'm very fast, but I want you to understand this. When we are creating the matrix, we always start with the rows, then followed by the column. The very same way when we are displaying the matrix, you realize for the side of the rows, we have 1, 2, 3, 1, then comma. Now this comma represent the column. There is nothing here, but it actually represents the column where the element belongs. So this is the first row. This element is in the first row, first column. This element is in the first row, second column. This element is in the first row, third column. So if I combine in terms of column and rows, you realize this element, particular element here, is actually in the 1, 3. That is its position, 1, 3. That is why you can see we have a comma here, and here we are starting with a comma, meaning there is another position here that it has already been defined here. So that is the trick you will be using to access the elements of a vector. So if I say from X I want 1 comma, and then I stop there, I'm expecting it to give me this, because 1 comma refers to the first row and all elements for the columns. Now for this one is all for the entire row and for the all columns. I don't know if you're getting that. So in simple terms, for matrices, since they are 2-dimensional, we need to specify both the row and the column and subsetting. So for instance, assuming I want to access the element 1, 2 here, those elements. Now these elements 1, 2, they are both okay. Let's not start with that. That one will be a bit tricky, not tricky as such, but let's say we want to access 2. Now 2 is in the first column, first row and second column. So I'll need the name of the matrix. The matrix is capital X, then the square bracket, the column which is 1, then comma the row which is 2, and we run that. So it will give me 2, which is this element, which is that element. Now suppose now I want the entire row. Now the whole row here is actually the first row, and for all columns. Now because it is for all columns, now we put a comma to represent all. So to access that, I'll have capital X, I open the bracket, then 1 comma, and we run that, and it is giving me the entire row. The entire row. Now what about if I want an entire column like this one, the last one here, this that is the 3 3, this one here, these elements, I hope you can see that. We want this, so it is again the entire column. So I have X, capital X. Now for the rows, because I want 3 6 4, I want from each row, so I'll just put a comma and then say 3, and when I run that, it is giving me the entire column. Though you can see the elements is as if they are listed as a row, but actually it's a column. Now let's go back. What I was saying is a bit hard, but no, it's not. I now want to access these first 2 elements. That is, they are both in the first row. Now one is in the second column and first column. So how am I going to do that? Well, there are a number of ways. Number 1, this is the first approach. For the rows, there is no argument. They are both in the first. Then we put a comma. Now, for the columns, we are moving from column 1 to column 2. So one way to do that is to say from column 1 to column 2. And when I run that, it will give me the output, the desired elements. Now another way to do it, I can say from that matrix X in column 1, then you put a comma. I want the first and the second. Now I can list them. I can use the the combine function and say the first one and the second, and I run that. It will still give me the same. Are you seeing that? Now another method, or rather another approach we can do it is actually, when I look at this, okay, it is for the same, for the entire row, but now we are leaving the last row, the last column out here. So instead of listing the 2, I can just say for the entire row, but exclude the last column. So I'll have X, and I say for the entire row, but not for the column, minus the last one, the third, and it will give me the same. So it's up to you now to decide, but it's always good to figure out various ways that you can access the elements. So back to you on studio. Now where is studio? I I want to formulate, you guys will be telling me the commands. You guys will tell me how to access the elements as I ask some questions. So we are starting with, here we are mentioning names. We are using this matrix capital X. Now, let me check from my list who is coming first. You guys are not lucky. Oh, the other members decided to join another class on the day. I mean, the day class is still behind. But we will combine the class as we proceed. So Mr. Rashid is the first one. Now I want Rashid to tell us the command, or rather how we can access these elements. Kindly, if you can try, Mr. Rashid.
Okay, so we will type X, the capital X,
Capital X,
the square brackets.
the square bracket.
You said 5 and 6.
Yes, 5 and 6.
So they are in the second row, so it will be 2, comma.
2, comma.
Then they are in the second and the third column, so it will be 2. Type 2.
2.
Full colon, then 3.
Full colon 3. Perfect.
Yes.
Thank you, Mr. Rashid. So we are going to Mary. Mary, I want you to assist me. We want to get, now should I give her complicated? Okay, let me see. Well, let's just start small. So Mary, I want these two, 6 and 9. 6 and 9. I hope Mary is with us.
Okay. You type X,
X,
square brackets,
square bracket,
comma,
comma,
3,
3,
comma,
comma,
2 full colon 3.
2,
Full colon
full colon
3.
3. Like that.
Yeah.
And then I run that. And it is telling me incorrect number of dimensions. Mary, your command is not correct. It is saying incorrect number of dimensions. Mr. Saif, can you assist her? Because of time. Yes, please, Mr. Saif, kindly proceed. I see you are using the chat. Seems like you have an issue with the microphone. You can type the command as well. Okay, here is the matrix, Mr. Safe. We want to access 6 and 9. Mary, did I say 6 and 9?
Yeah.
Yes, here. These last two, 6 and 9. Sorry for that. So as we wait for Safe to type the command, Mary,
Yes.
you need to take note about one thing.
Mm-hmm.
We are dealing with rows and columns, okay?
Yeah.
And from here, when we are starting to access the elements, you can see that we have only one comma. Can you see that?
Yeah.
Now the reason as to why we have only one comma is because we are separating the rows and the columns. So whatever you do or before the comma, R takes it to be the column or the columns you want to access. And after the comma, before the comma is the row or rows that you want to access. And after the comma is the column or the columns you want to access. So in whatever thinking you'll do, one thing you should take note is that you only have one comma separating the rows and the columns. So here you have a problem, actually number one, that you have 3 columns. Two commas. So it is like you're accessing all rows here and 3 columns. Now we don't know what is this representing. But I don't know if Safe is able to help us out. Yes, Safe. Maybe Safe has some issues with the internet or the microphone.
Can I help?
Yes, please.
Okay. So X,
Capital
X,
X,
square bracket.
square bracket.
So you said it's 6 and 9.
6 and 9, yes, Mr. Rashid.
So 6 and 9, they're in the same column but different rows.
Yes.
And as you said, we're supposed to start with rows, then to go to columns.
Yes.
So it should be 2.
2.
Then full colon. 3.
3.
Then comma. Then 3.
3. Perfect. Perfect. Even before I ran that, it's very perfect. 6 and 9. So you can see the secret Mr. Rashid was doing. Number one, he understands that we will always start with the rows and then comma the columns. So what he is doing is to first identify the rows that he wants before he can put a comma and proceed to the columns. So he was looking at 6 and 9 and he's saying now it is 2 comma full colon 3, meaning 2 to 3 and then comma 3, and that is perfect. And another way, if you don't want to use the full colon, you can say capital X. Now for the columns, I mean for the rows, like Mr. Rashid was saying, we want 2 and 3. You can use a combined function. We said when you are listing more than one, you use the combined function. So I want the second and the third. No, those are for the rows. The second and the third. Then outside that, because those are the rows, they are all in third column. And when you run that, it will give you the very same answer. Which is as good as saying, when I look at these elements here, you see it is 6 and 9. So they are in the second and third rows. Now which means we are only excluding 3 that is in the first row. So for the rows, I can say, actually, I want everything for the rows except the first one. So -1. Then I put a comma. Now for the column, I only want 3. So for the column, you are subtracting what you don't want to access. And then for the column, you just put the column. The reason as to why we don't bother about we are having the entire column is because these two are being selected in terms of rows. So when we run that, it will still give us the same, very same answer. Very same answer.
Question.
Yes, please.
Since you are saying that we can exclude by putting a minus, saying
Yes.
that whatever you don't want, can you do for both, for the rows and the columns?
Yes, we can. Yes, we can, Mr. Rashid. So how can we actually, let's do that. So we don't want the first row. Now for the column,
So you don't want the first column.
not the first and the second. Are you seeing that?
Yeah.
We don't want the first and the second. No, because there are two, you'll have to use the combined function. So now remove, because there are two, I'm using the combined function, the first and the second. And when we run, it still give the same.
Thank you.
Yeah, thank you also for bringing that aspect. So there are many ways of killing a rat. We can burn the entire house. And that is it. So because we still have a challenge in accessing, I'm assuming we still have a challenge. I'm going a second round. And members will be giving the procedure. Still we are using the same matrix. So, or someone is having a question. Mary, you have a question?
No.
Okay. Now that you don't, I do. So now this time we are going bottom up. I'm starting with Saif, then Mary, then Rashid. So, Mr. Saif, I want to access these elements. I mean 5, 6, 8, 9. 5, 6, 8, 9. 5, 6, 8, 9. These ones here. Forget about this 7. I want 5, 6, 8, 9. I know if you can't speak, you can type. Five, 6, 8, and 9. Just give it a try. As Saifu is trying to figure out let's also try to figure out. In fact, we have more than okay, we have at least 3 approaches. So maybe whoever is having an approach to give us before the other one figures the other approach. I think that way we'll move fast.
Okay, the first approach.
Yes, Mr. Rashid.
So capital X,
Capital X,
square brackets,
the square bracket,
2 full
2
colon 3,
full colon 3,
comma, 2 full colon 3.
2 full colon 3.
Yes.
I've not even checked that. Sorry?
Yeah, that's it. That's it.
Okay. Yeah, it is. 5, 6, 8, 9. It is. So another approach maybe, Mr. Safe, that you have thought of. I know you'll say it is the same. Any other approach? So
Welcome back, sir.
thank you. So where are you now? You are done?
Yes, I was giving you the other approach.
Okay.
Yeah.
So what is the other approach?
The other approach is X into the square brackets. You are calling it what were you calling the
We want
function?
to get
Is that
5, 6, 8, 9.
No, there was a name you are using to call the function.
Oh, combine.
The C, the one.
Combine.
Yes, the combined. So
The
C
combined function.
brackets 2,
2,
comma 3.
3.
Then outside the combined, comma, another combined,
another combined function,
2, comma 3.
2, 3. Wow.
Yes.
That is a genius thinking. Wow. That's it.
Yes.
That's interesting, Mr. Rashid.
And then the last one.
Another approach.
You're saying what? Yes, the third one.
Okay.
So X, brackets, the square brackets,
yes,
excluding row 1,
excluding 1,
comma, excluding column 1.
excluding column 1. Marvelous. All those are the approaches. That is very nice. I don't know if we are getting that. Mary, are you getting that? And Mr. Safe?
Yes.
Yeah, I'm sure it requires looking at it from another dimension, but the fact is that is to understand what you really want, what you're doing, like which elements to access, and figure out the best approach. Now you see, whenever you're trying to figure out the approaches, or rather the approach that you're going to use, basically there are two. that is what you want to get, so you list the column and the rows, or what you need to exclude so that you remain with what you want. I think that is the secret. I think that is the secret. Now, having discussing that, I want us to discuss something on operation of matrices. But before doing that, let me see if there's another way I can ask about something. But I know you guys will get it. Okay. I think we have understand how to access the elements. So we want to look at other ways of creating matrices. The first case, we were having a vector and we were converting it, or rather from the vector we were forming a matrix. Then the other way, we just went and created a matrix. Now at times we can have several vectors, and now to form a matrix we need to combine those vectors to form a matrix. So like we have one matrix, we have a vector. Now from that vector we want to create a matrix. That is the first case we were doing. But now maybe we have two or more vectors, then we want to form a matrix out of those two vectors. Now you see, the vectors can easily be combined into rows and columns and form one matrix. Because what we were what we were forming, the way we were forming the matrix at first year, we were basically converting this matrix, this vector into rows and columns. So suppose we have two vectors already and we want to form a matrix, one matrix. Is there a way maybe we can just coalesce the two vectors so that we come up with a matrix, or rather combine the two, but in such a way that we are creating a vector, or rather we are creating a matrix, sorry. From the vector, we are combining two vectors to create a matrix. That is what we want to do. Now, assuming we have two matrices, vectors, from which now we are to form a matrix. Now we have this first, vector. Now we have used the x. Have we used y somewhere? We have used y, but not as much. So let's say we have this vector y, and we say the vector y, because I'm lazy of, let's just say the vector y is of the elements from 1 to 9. That is the vector y. So that when we call y, we have the elements 1 to 9. Now, let z be now another vector. Mr. Rashid, we said in the other last class we were saying that we can use the equal sign to assign values to a vector, or rather a variable, as well as the less than or equal to sign. They'll still work the same, but there is an advantage of using the less than or equal to. We will talk about that as we proceed. Now let's z be, we can just say, okay, I don't want to create more vectors, new vectors as such, but I'm trying as much as possible to bring the aspect of functions as well, so that you guys can understand some functions. So I'll use this reverse function. Now reverse function basically changes the arrangements of variables. Like okay, if you put a question mark here and ask for the documentation, you will be able to see more about the reverse function and its use. That function didn't really okay, it is taken to be one function. That is why, you know, we have z there. But basically, the reverse function is used to reverse the elements of a vector or even a matrix. Before R was advanced, this reverse function was actually used to, order the elements in a certain order. Suppose now we have elements that are not arranged as such. The reverse function was also used to do some sorting of elements. That is before the sort function itself was introduced. Now we are not using that anymore because we have the sort function and the order function as well. So reverse function, let's just say now the vector z is the reverse of y. So if y is starting from 1 to 9, then z will be 9 to 1. That is what I mean. So we run that. Now when I call z, you see we have 9 to 1. The other one is 1 to 9. Now what we want to do is we want to form elements using these two vectors. We want to form elements using these two vectors. Now you realize I can decide and say, because these two vectors are of the same dimension, they are of the same length. You can see they are of the same length, 1 to 9 and 9 to 1. Now I can decide and say I want a matrix. These two vectors can be used to form a matrix. I want a matrix so that this will be my first row and this will be my second row. Are you seeing that? So that it will have 2 rows now with 9 columns as such. So you realize, in simple terms, these two vectors are combined row-wise. They are combined row-wise because this will be my first row in that case and this will be my second row. So in forming that matrix, now these two vectors are being combined row-wise. Now instead of doing that using a matrix and starting to specify the number of rows and columns and all that, we can actually use a simple method of combining these two vectors row-wise and come up with a matrix. So what I'll do, or rather what we'll do, we'll use what we call the R bind, which in simple terms is the row bind. Like we are telling R, take these two rows, combine them row-wise. That is, we are having this as our first row, then down here have this as our second row. That is row bind. So we'll use R bind. So when I come here, I'll say R bind, and this function is in this R. Now bind Y and Z to form a matrix. And when we run that, because we have not assigned that to a variable, or rather we have not assigned that matrix to a name, we automatically have our matrix. So for such a case, there is no need of even using the matrix function and all that, because we want to combine those two matrices so that they are combined row-wise. So we will use the R bind. And you can see this is literally my Y, and it is even given the name Y because it is row bind. So the name of the rows will be the name of the variables, and now the columns will be assigned indices, that is 1 all the way to 9. So literally this is my my Y, and this one is my Z, and this one is my Z. Now what about if I didn't want them to be bounded, or rather to be in that order now as rows, but I wanted to have a matrix such that I have the values of Y as a column and the values of Z as a column? in which most of the cases will have that. Now, in order to do that, again, we simply use another function which now binds the two vectors, but now this time round, it is binding them column-wise, and the function is cbind, which literally is binding these, or rather combining the objects based on the columns. So I'll say now bind my y comma z, but now it's cbind, and when we execute that, we have the same matrix, same elements, but now forming a matrix that is column wise. So we have 1 2 3 all the way to 9, and now z we have 9 to 1. So that is other simple approaches that we can actually use to make a matrix from vectors. And now you can see that when we are doing that, the name of the columns now is the name of the variables. So that is also another approach. I don't know if you guys are getting that. Is it clear, or someone is having a question? Now, to access the elements, we will still use
Question.
the same. Sorry?
I have a question.
Kindly ask.
So far, I've understood whatever you have just taught.
Yes.
I've just maybe an inquiry. Can we, like, is it possible to bind them, but one as a row and one as a column?
Like we bind such that we have
Y is a column and
Y as a column,
Z.
Z
Is it possible?
as a row.
Yeah. Or it's not?
Have you, okay, this is just a joke.
Yes.
Mr. Rashid, have you ever seen a matrix like that?
I'm not a mathematician. I don't know.
Okay, like now a matrix need to have what we call the dimension. That is the number of rows and the number of columns.
Okay.
Now you see here it's two-dimensional. We have rows and columns. Now what you're trying to say is like you're saying we have 1 to 9 like this, and then we have 9 going this way.
Oh, I understood.
Now what will happen at the center? That is not a matrix.
Okay.
Yeah.
Thank you.
Okay. Any other question? Now I want us now to go ahead and look at what we call matrix operation. And because of that, we will use let's form matrices now. Okay, X and Y are vectors in this case, so let's form matrices. Y and Z. Forget about these C bind and all that. We're not going to use those matrices, because the fact remains to be that when it comes to operations of matrices, there is always the aspect of mathematics that in order to do an operation for matrices, 2 or more matrices, the matrices need to be compatible for that particular operation. Like for instance, when we are doing what we call addition of matrices, we want to take 2 matrices and sum them so that we can have a resultant matrix from the sum. Now, one of the rules in order to do the addition is that the matrices must be of the same order. That is, the number of rows in the first matrix should be equal to the number of rows in the second matrix, as well as the columns. So that is why I'm saying let's try to formulate matrices so that they are compatible, with the various operations, then see how we can do the operations now using R. So I want us to create our matrix. Let's create our matrix X. Now our matrix X, let's just say the matrix X is the matrix of Y. Now Y was starting 1 to 9 and is a 3 by 3 matrix, 3 rows and 3 columns. So we have our X, and let's have another matrix Y, and say that Y now is the matrix, don't get confused, is the matrix now Z. Now remember Z is 9 to 1, so it is also a 3 by 3, and we run that. So let's call our matrix X. It is 1, 2, 3 row wise, and now our matrix Y, it is now starting 9, 8 like that. Those two are awesome, even easy to see the operations and all that. I hope we all have the matrices. If you are confused in forming, just let me know. So if you have the matrices, kindly type 1. If not, type 0. If you have the matrices, kindly type 1 on the chat. If not, just type 0 and we see how we can assist you. Maybe there is one command that you didn't execute, in creating the matrices. Like maybe you don't have Z and you don't have Y. If you have the matrix, kindly type 1, or rather the matrices, that is X and Y, and they are just like mine. Kindly type 1. I see Mr. Rashid, Mr. Saif. We are good to go. So that is nice. So let's go back to now looking at the various operations that we can do with the matrices. Now, one operation that we all know is the addition. And like I was saying, to add matrices, the matrices must have the same number of rows and the same number of columns. Because actually, in mathematics, when we are adding two matrices, what is happening is that we are adding the corresponding elements of the matrix to have our final matrix. This is what is happening. This is the first element in the first row, first column. So this element will be added to the element in the second matrix in the first row, first column. So the resultant matrix, the first row, the first column, will be the sum of this and that. Now the second, it is 2 now plus 8, and that is now it is adding those corresponding elements. So to do that with R is very simple, because just like the normal operation, we just say X plus Y. We just say X plus Y. And you can see we have 10, 10, 10, which is actually correct, because when I look here, I have 1 plus 9, 10, 2 plus 8, 10, 3 plus 7, 10, 4 plus 6, 10, and you can see that I reasonably created that matrix so that we can easily monitor that. So that is addition. There is nothing to discuss about that. That is how we do the operation. Now again, the same way we do we do subtraction. So subtraction will be just X minus Y, and it is actually subtracting element to the corresponding elements, or rather from the corresponding elements, because I have 1 minus 9 negative 8, 2 minus 8 negative 6, and all that. So that is the operation when it comes to subtraction. Now, what is quite interesting, or rather what is the problem, is when it comes to multiplication. Because we all know when it comes to multiplication and in mathematics, I know that we have mathematician in the house. When we are multiplying two matrices, basically what is happening is that we are taking a row like this one, the first row, we are multiplying by the column and we sum that. Then take another row, multiply by the column and sum that. So for this case, we'll take this row, this first row, multiply by this column. So it will be 9 multiplied by 1 plus 4 multiplied by 8, 7 plus 7 multiplied by 7. Then we sum that. So that is one element. Then the very same row, we move to the second column. So 1 plus 6, 1 times 6 plus 4 times 5 plus 7 times 8. We sum that. That is one element. So the question is, how do we do that with R? Now you realize when we just say x multiplied by, remember multiplication is represented by asterisk, and then we say multiply by y, and we run that. Now you realize that is not really what is happening. That is not what it is happening. Instead, this one is just a multiplication of the corresponding elements. Because when we come to this matrix here, you can see our x and our y. We are actually taking 1 times 1, which is 8. 1 times 1 is 8. Okay, 1 times 9, which is 9. 2 times 6, which is 16. 3 times 7, which is 21. Which is just happening here. They're just multiplying the corresponding elements. Now, that is not what we are supposed to do. That is not the multiplication of matrices when it comes to mathematics. So the correct approach, therefore, or rather the correct way to multiply matrices is to use this operator, or rather to use this multiplication symbol. So we will say it is x multiply by, and this is how we write multiplication, multiply by y. Now that will do the matrix multiplication we are talking about, taking the rows and the columns, summing them to have one element at a time. So when I run that, now that will give us the correct sum. And if you really doubt that, you can even try to do it at your own free time, and you'll see that that is actually the way we are supposed to multiply matrices, but not the other way. Not the other way. Not the other way. So again, we realize we also have some important functions as far as matrices are concerned. We have these functions that will help us to compute some important elements of matrices. Like for instance, you realize in most of the cases, when maybe we try to solve matrices, at one point there is the issue of coming up with what we call the determinant. I hope we all can remember about determinant, and if not, basically a determinant is, let's say the determinant of the matrix X is that one matrix, which when we take X and we multiply it by its determinant, is a determinant of, is it a determinant of a matrix, or what is it? Okay, we have the determinant, we have the inverse, and what do we have? Mathematician Mary, what do we have? We have inverse, we have determinant, and what else? You see, the fact is that we can't separate mathematics and statistics from machine learning. From this, we will have to discuss those. So basically, I can remember that we have, okay, I was very correct. It's the inverse. It's the inverse of a matrix. Okay, we have the determinant, then we have the transpose, and we have the inverse. We'll discuss all that. Now, we all know that the determinant of a matrix is the main diagonal, the product of the main diagonal minus the product of the other diagonal. This is what I'm talking about. We did that in high school. So it is the product of the main diagonal, this one here, minus the product of the other diagonal. That is the determinant. Now the inverse is where now the rows, these rows becomes the columns, and the columns becomes the rows. That is the transpose, not the the inverse, but the transpose. Now the inverse of a matrix is the transpose divided by the determinant. It is the transpose divided by the determinant. Now the inverse is what the answer, what you are getting. And normally one property about the inverse is that whenever we take the matrix and we multiply by the inverse, it will give us what we call an identity matrix. An identity matrix. Now someone is asking, what is an identity matrix? An identity matrix is basically that one matrix which operates like number one. That is, when we multiply by a number, the answer is just the number. That is an identity matrix. So the reason why I'm trying to bring all these aspects is that R is actually having some functions or other functions that helps us to avoid all those calculations using a pen and just get whatever we want. Now, like for instance, we can get the transpose of a matrix by using the transpose function. This is the function. This is the function we're talking about. We can actually just use that function. Okay, I don't want to write the function down here. I've written the function in the console, but let's write it here. So we can use this function to get the inverse of the transpose. This is the function I'm talking about. I really don't know if there's a documentation of this, but it should be there. Matrix transpose. You can see this function is also in base R, and it gives the matrix, it gives the transpose of the matrix. So all you have to do is just to pass the matrix there. So when you pass the matrix, you get its inverse. Now let's look at the matrix X. Let me just call the matrix X again, and you can see the difference. Now this is the matrix, the initial matrix that we had. Now look at the rows. Look at this column is now the row here. I mean, this row is not the column here. Look at this row is not the column here. There is the transpose. Now when we want to get the inverse of a matrix, when we want to get the inverse of the matrix, we'll basically say solve, and you pass the matrix. So solve for X, and this one will give us what we call the transpose. Now something interesting is happening here. It is telling us solve in dot. There is an error. There is an error, and it is telling me the mu, which is basically the matrix 3 by 3, is equals to 0. Something interesting here. What could be the issue with the matrix X? What is the issue with the matrix X? Who can try? Who can guess? Is it guessing? No, it should not be guessing. Who is trying? Something is not happening here. And let me just confirm that, and I'll tell you. Okay, I'm using a calculator. Don't say where are you confirming now. Okay. So who is seeing that? Mary, I have a question for you.
Yes.
Mary, can you hear me?
Yes.
What is a singular matrix?
Singular.
If you can remember.
Uh-huh.
What is a singular matrix? Or anyone who can remember?
Can I try? Although I'm not an expert.
Nguvu kwani?
Yes, Darashi.
Is it that I suppose it gives you a determinant is 0?
It's
A singular matrix has a determinant of a single matrix is 0. If a matrix has a determinant of 0.
perfect. Now, that is a singular matrix. A singular matrix is one whose determinant is a 0. That is a singular matrix. So they say a matrix is said to be singular if and only if its determinant is 0. That is it real analysis, Mary? I think it's real analysis. Now, the reason as to why we are having a 0 here, as I was explaining, I was saying that to get the inverse of the matrix, we first need to get the determinant, then get the transpose. Then take the transpose divided by the determinant. Now, here we are having a determinant of a 0, which means that the transpose is now being divided by a 0. That is where we are getting an error. You see, when we take a number divided by a 0, there is it will give you an error. It's a very big number. So the reason as to why we are having an error in this code is not that our code is not correct, but the fact that whatever we are dealing with is a singular matrix which has no determinant. So in simple terms, it has no inverse. I don't know if you guys are getting that. So maybe to just clear the doubt, we can come up with another matrix and then get its inverse and see if it will give us if we take the matrix now multiply by the inverse, it gives us an identity matrix. So let's have a matrix Z. Let's have a matrix Z. Now Z is again, I don't want to have a random matrix that maybe will give us a determinant of 0. Let me try to get a matrix that has an inverse. So let's have this matrix, a 2 by 2 matrix. Z is a matrix, of course. So just say matrix. Then we will list the element using a combine function. So we say 2, comma 7, comma 1, comma 4. Then we say it's a 2 by 2. So 2 rows, 2 columns, and we run that. Then we call Z. So Z is 2. Yeah. That one should have an inverse. Yeah. I think it should have an inverse. So Let's say now solve for z. Now when we solve for z, we are getting that as the inverse. Now when we take this inverse, we multiply it by the matrix we are expecting to give us a singular matrix. That is a matrix that behaves like number 1. Now a singular matrix is basically the diagonal matrix. It has 1 at the diagonal and 0 0 elsewhere. So we're expecting it to give us 1 0 0 1. That is column wise. So let's multiply and see. So we'll say, because we didn't assign this a variable, and because I'm lazy, I'll just multiply z there. But that is not the multiplication we say. So we are using this multiplication, multiply by z itself. What are we getting? Oh, perfect. It is giving us a singular matrix, or rather an identity matrix that is behaving like number 1. So yes, the solve function is actually giving us the inverse of a matrix. And when you take the inverse, you multiply by the matrix, it is giving us an identity, or rather a diagonal matrix. So that is what I wanted to tell you. But not always, it's not always, you see, I'm trying to introduce as more functions as possible. It's not always that when we take a matrix like this one and we multiply it by its inverse, it will give us exactly an identity matrix like this one. Not always the case, because of some computational errors, not errors but truncation, approximation and errors, that is it. Maybe rounding off and all that. So how now can we prove that this is actually the inverse and it is giving us an identity matrix? So I want us to do a practical example that now will help us to see that. So maybe we redefine another matrix. Let's redefine another matrix. So let's have another matrix. Now this time around, let's call it capital Z. You see, we are spending almost the entire lesson with matrices, but it's still okay. We can finish on matrices. Then the other time we'll be looking at vectors. Not vectors, but data frames. We are the most important. So let's redefine a matrix Z, now capital Z, and say one now that Z is a matrix. And it is made up of the following elements. We use the concatenating function, of course. So we have 9, 2, negative 3, 2, 4, negative 2. We want to have 3 by 3 matrix. So negative 2, negative 3, and negative 2, and finally 16. Now because it is a 3 by 3, you can just put a comma and say 3 to represent the rows and the column. And let's say by rows. So by row equal to true. Let's say it, just say it, and we run that. Oh, there's an issue. I bet it's the element. They are not enough. we have 9, 2, 3, then 2, 4, then -2, -3, -2. Let's say this is 16. What else is okay? How many are they? 1, 2, 3, 1, 2, 3, 1, 2. There are many. We need to remove at least one. So 9, 2, -3, 2, 4, -2, -3, -2, 16. But I can see we have 3, we have another 3, and we have another 3. So what is the problem? Okay, let's say just say 3 by 3 here. 3 by 3. Let's say 3 by 3. Are my elements more, or what is happening? It seems like I'm leaving one element out. Okay, this is 3. This is 3. Oh, I didn't put a comma here, so it is taking it to be one element. That is the problem. Okay, that is it. You see, you can spend the whole night looking for a comma, and you are literally not seeing the comma. Just like how programmers spend the whole night looking for a semicolon, and they are not seeing that. And they are spending the entire night trying to think outside the box, only to realize in the morning, after spending the whole night, they are missing a semicolon somewhere. How do you even feel? I can't imagine. So when we call Z, we have that. So now we want to get the inverse of Z. So we'll say solve for Z. Now that is the inverse for Z. The question is, when I multiply this inverse of Z, look the way it is, will I get an identity matrix? But why should we ask such a question? Let's do it and see. So I'll say multiply by Z itself. And when we do, we are not getting an identity matrix. We are getting another sophisticated matrix we cannot even explain. But the rule of the game, or rather the rule is, whenever we take an inverse of a matrix, like this one, and we multiply it with the matrix itself, it must and it will always give us an identity matrix. So this means that this one is actually an identity matrix. And you can even note that, you see, we have 1, 1, 1. Now here we have 8 point, but now it is raised to -17. So we are going backwards 17 steps. But someone could say, my friend, you are now trying to give some validation that this is an identity matrix, but it's literally not. Now I can tell him, let's then create an identity matrix, then equate it, or ask R to compare this if it is equal to an identity matrix. And in this case, it is a diagonal matrix which is 3-dimensional, or rather an identity matrix that is 3-dimensional. So let's create an identity matrix, then compare it. If it is they are equal, then it means it is an identity matrix. Or rather, if they are equivalent, then it is an identity matrix. Or we can compare and tell R to use logic such that if it is actually an identity matrix, it returns true. So let's create that identity matrix. We can simply say, because it is a diagonal matrix, we can use the diagonal function and say diagonal, diagonal of a 3 by 3 matrix, and that is it. So that one is an identity matrix, a 3 by 3 identity matrix. There is no argument about that. Now the point here is to compare if this matrix is equivalent to this, because for a 3 by 3 matrix, this is how the identity matrix is. So we need to compare these two. Now how do we do that? Now there are several ways. I know someone will say, I'll say this is equals to this. Now what will you be doing? You'll be just reassigning. Now there are several ways of doing it, but the beauty is that R has a function known as equal, or rather all equal. Now all equal is used to compare if all the elements, or rather the arguments passed in that function are equal. So I can say all dot equal, that is the function. You can even ask for the documentation. Now this function, literally what it does is that it compares if the elements, or rather the arguments passed there, the target and the current arguments, if they are passed there, they are equal, then it will return a logic true. If they are not, then it will return a false. So let's test if the solve for z, remember we are comparing this, we are comparing this if it is equal to this. So solve for z, then multiplied by its matrix itself, that is z. Okay, this one is supposed to be capital Z. If we find the determinant of z, the inverse of z, then multiply by itself. Is it equal, or rather, to an identity matrix of 3-dimensional? Are you seeing that? Or we could have assigned these to variables and we only pass the variables here, but still in the same way. So when I run that, it is telling me true, the two are equal. The two are equal. So actually this one is equal to that. So it is true that this is the inverse, because when we take this, this is the inverse for this particular matrix, because when we take this multiply by this, it is giving us this, which we have just confirmed is just like this, an identity matrix. So that is also important to take note. At times you will not get a perfect identity matrix like that, but there are several ways of getting to prove if it's really an identity matrix. Again, we have several other functions, like you can have a function to check the dimension of a vector. Now the function name is the dimension of the die. So when you run that and say the dimension of x, you can use any vector now. When you run that, to tell you that this function, this vector is a 3 by 3 vector. That is the dimension. Now another two important functions that we normally use is what we call the row sum and the column sum. At times you just want, or rather you want to get the sum of these column variables, like maybe these last 3, 7, 8 and 9, or maybe you want to get the row sum, so we want to get the sum of this. So how am I going to do that? Should I access the element one by one? Sorry for that. Should I access the element one by one and find the sum, or is there a shortcut? Yeah, there is a shortcut, and the shortcut to do that is to use what we call the row sum and the column sum. The row sum and the column sum. So you can just say the row sum, and this one will return the sum in the matrix. Okay, which matrix did I run? Okay, it's the function that is wrong, not the matrix actually. It is supposed to be the row sums. You see, there are very many functions. The row sums, that is the one from row and column sums and means in R. For matrices. I'm also tired for speaking that long. So when we say X, we are getting the row sums. Remember, it is summing for the various rows. So there are 3 rows, we're getting 3 sums. I don't know if this is really the matrix I've used. I bet is this capital X or small x, but I can just copy the matrix so that we can see. Oh, and it is even row, so it is correct. There is no need. So now for the column sum, we can use the column sums as well to get the column sum. So we will run the column sums for X, and you have it. Again, you can get the column mean and the row mean. Mind you, this is very, very important when we are doing analysis. At times it is good to compute the column sums and the row sums, because there are some aspects that as we proceed, you'll see them and you'll even understand better. So you can also get the row mean. You don't have to find the sum and then come and compute the means. You can get the row means. Remember, it's means because there are several rows, and it's sums because there are several columns and rows. As well, you can get the column. You can get the column means. You can get the column means for X. So those are simple functions that you can understand. There is no need of doing explanation about that. I don't know if you guys still understand, or you guys have switched off. I remember the other time only to realize members are dead asleep and I was speaking alone. Guys, are we still here?
Yes.
I bet you guys are very tired now.
Yes.
Yeah, I know Mary would say yes. So we can just stop here for today, or on matrices. You'll have time, go through the video. I'll send the recording. If you have any question, feel free to ask. I think we'll start from here next time. We'll finish on some few aspects maybe that I think are important to mention. But then make sure you don't miss the next class, because that is data frame, or other data frames. And in most of the cases, when we import our files, our data files in R, they will always come in the format of a data frame. So make sure you don't miss that. Make sure you don't miss that. So unless there is any question, otherwise we can stop here for tonight. Any question, any point that is not clear? Very well, then good night.